So let's keep talking about conic sections. In our last video, we mentioned this parabola that has the point as its focus and the line as its directrix. But the other conic sections have interesting geometrical properties too. And some of these properties were discovered by the French mathematician, I believe he was French, Dandelin, in, I think, the 19th century. But before I get into that, there's something else. There's yet another characterization of some of the conic sections, and I haven't told you about it yet. So there's another way of characterizing an ellipse, which is that if you take 2 points, A and B, and then if you take some number sigma that is greater than the distance between them, then the locus of all the points P, such that PA plus PB equals sigma, is an ellipse. Because it looks something like this. Not a very accurate diagram, but. And these points would normally be called the foci of the ellipse. I know it's perhaps confusing to have the same, and each one is a focus. Yes, I know, rather confusing to have the same word focus for two different things in the case of two different conic sections, but whatever. And so it goes around in a loop. And so that's the ellipse. Not going to prove it here, but that's another characterization of the ellipse. And then the hyperbola has a similar characterization, where you take 2 points A and B, and some number sigma, positive, and less than the distance between them. And then you take the locus of all points P in the plane, such that the absolute value of the difference between PA and PB equals sigma. And then you get a hyperbola this way. Something like this. And again, not going to prove it here. And I believe you would again call these the foci of the ellipse. Hyperbola, I mean. So, what Dandelin did is take this cone, intersect it with a plane to get an ellipse. So, why is this ellipse defined by the cone the same ellipse that you get when you write this locus property? What are these points A and B? And what Dandelin found is that you get them as if you inscribe two spheres in the cone tangent to the plane. And we let these 2 points be A and B. And it turns out that these are the foci of the ellipse. And this number sigma is the distance of the tangent between them. And just if you ignore the plane, then we have all this. Then we've got a lot of symmetry in the picture. So it's clear that anywhere around the ring you take the tangent, it's got the same length. And this will be important in what follows. In 3 dimensions, it's a lot nicer than this 2-dimensional representation. So why does it stay constant for all the points on this ring, on this ellipse? Well, take any point P, then the distance PA, the sphere is tangent to the plane, so PA, the line segment, or I guess we'll say the line PA, is also tangent to the sphere, this little sphere, and then PB is tangent to the big sphere at B. But any two tangents from a sphere to a point have the same length. Because, for example, because if the center of our sphere is O and its radius is r, and you take any point P and draw a tangent, then you get a right triangle. And so the length of the tangent, and its hypotenuse is fixed length, and its one leg is fixed length. So the other leg has fixed length. So and this length is the length of any tangent from P to the sphere. So the length PA is also the length of the tangent if we draw the line segment through P along the surface of the cone, tangent to a point on the upper circle. And similarly, if we take PB and draw it down, you get a point on the lower circle. But now, PA plus PB, these two line segments go together to make this plus this, which is this segment, which is constant no matter where we put P. And so this is where we get this nice explanation for the foci of an ellipse. And there's more I want to say, because I want to briefly mention how this would apply to other types of conic sections, and then in more videos I want to talk about the nice properties that parabolas have. And I can get to all that and more, so stick around for Conic Sections Part 4. Thank you for watching, and I hope you follow me on Twitter at Luke_Robitaille. Thank you!